Hello students, good morning. In the last class we discussed the concept of finding unknown frequency using the loading method. When a tuning fork is loaded with some wax, its frequency will decrease. By using that method, how to find the unknown frequency we discussed in the last class. In today's class, let us see how to find the unknown frequency of a tuning fork by filing method. There is a filing method to find unknown frequency. Let us consider two tuning forks, say tuning fork A of frequency f A and tuning fork B of frequency E of B. These are the two tuning forks. So, out of which this value is a known frequency. This is a known frequency. One value will be given in the problem. So, let me take this as the given frequency and this is the unknown frequency. So, like this two tuning forks they will mention in the problem. And now, before going to discuss the actual method, so let me tell you what will happen on filing a tuning fork. So, filing means like rubbing a tuning fork prong with the sandpaper. So, that means that the thickness of the tuning fork prongs will decrease. So, on filing the inertia of tuning forks will decrease. So, that the frequency, so frequency of a tuning fork generally inversely proportional to inertia of the prongs. So, as on filing the inertia will decrease, frequency will increase. So, on filing, so remember this point, on filing a tuning fork, its frequency increases. So, this is the thing you have to keep in mind while doing problems on this method. So, on filing its frequency will increase. Now, let us discuss how to find the unknown frequency by using this method. Suppose the prongs of this unknown tuning fork. So, this is the tuning fork whose frequency is unknown. If its prongs are filed, so there are two cases we can discuss. That means it may be, so for suppose if initial number of beats f b is equals to f a difference e of b, we do not know which is greater, which is smaller in this case. Now, on filing two things may happen. One is number of beats may decrease or number of beats may increase. So, now let us see how to calculate the unknown frequency in each case. So, first so on filing, so here on filing tuning fork B. So, the first case may be number of beats decreased. If on filing, if number of beats decreased means initially some FB is the number of beats per second, that is frequency of beats. So, on filing one unknown tuning fork, number of beats are decreasing. So, if this is the case, the unknown tuning fork frequency FB is given by FA minus number of, that is beat frequency, initial beat frequency. So, tuning fork frequency, that is no given value minus the number of beats per second which are formed initially by the two tuning forks when they are sounded together. That is the first case. Suppose if number of beats are given increased. Second case, if number of beats increased on filing. If number of beats increased on filing the tuning fork B, then the unknown frequency FB is given by FA plus FB. Remember, the reason for this is here the tuning fork frequency FB less than FA and here FB greater than FA. So, that is what the method of finding unknown frequency using the filing method. Now, let us discuss one example for understanding the concept clearly. Tuning fork, a tuning fork of frequency some 285 Hz is sounded together with another tuning fork of unknown frequency producing 5 beats per second. 5 beats per second, and if the another tuning fork is filed, so that number of beats are decreased. So, here let FA, first tuning fork frequency FA, that is given value or known frequency, and let that unknown frequency is FB, which is to be found here. Now, beat frequency, number of beats per second on sounding the two tuning forks together initially is given, that is the 5 beats per second or 5 Hz. Okay. Now, the question is, if on filing the unknown tuning fork, if number of beats are decreased, then what will be the value of unknown frequency, that is a second tuning fork frequency, how much, that is what you have to find. So, now let us do. So, here FB you can take it directly. See, the first case it is, if number of beats decreased, unknown frequency is equal to given frequency minus number of beats formed initially when they are sounded together. So, that means here FB value is equals to given frequency value 285 plus number of minus number of beats formed is equals to 5. So, 285 minus 5, that is 280 Hz. So, like this you can do the problem directly if you remember these two cases. So, if number of bits are decreased, unknown frequency is equal to FA minus FB, that is given frequency minus number of beats per second, and if number of beats are increasing, then unknown frequency equal to given frequency plus here beat frequency. So, that is what the two cases. So, in the same problem, if number of beats are increased, for example, if I do this second one. So, if number of bits are given increased in the problem, that means the unknown frequency FB is equal to given frequency 285. So, here plus 5, it will be 290 Hz. 290 Hz. So, that is what the method of finding unknown frequency using filing method. Remember both the case. So, here the main thing you have to observe is either number of bits are decreasing or increasing on filing. So, if you identify that point, then you can easily solve the problem. Now, let us discuss one more example on the beats concept. So, this problem is one of the important methods related to beats. So, the problem is 64 tuning forks are arranged in series. So, 64 tuning forks, 64 tuning forks are arranged in a series, so that each produces 4 beats per second with the next one. That means 1, 2, 3, 4 and so on up to 64 tuning forks are there. So, in this case, each tuning fork produces 4 beats with the next tuning fork and so on. So, up to 64 tuning forks. Now, and also so here each tuning fork produces 4 beats per second with the next one, and another data given in the problem is the frequency of the last tuning fork is octave to the first tuning fork. The frequency of last tuning fork is octave to the first tuning fork, that is the condition. So, two conditions given in the problem. There are 64 tuning forks which are arranged in series and each producing 4 beats per second with the next tuning fork, and the last frequency, that is last tuning fork frequency, is octave to the first tuning fork frequency. Then find out, the question is find the frequency of 16th tuning fork. 16th tuning fork. So, this is the question completely. So, there are two conditions given in the problem and is asking to find the 16th tuning fork frequency. Now, let us see how to do this kind of problems. So, first let me consider the f. Let f is frequency of first tuning fork. So, frequency of first tuning fork is f, first tuning fork. Just apply the given conditions. The conditions are two conditions given. Each tuning fork is forming 4 beats with the next tuning fork, and the last tuning fork frequency is octave to the first frequency. Octave means 2 times the first frequency, that is the condition second one. Now, let us take the two conditions and solve it for f. So, let f is the first tuning fork frequency. So, then frequency of last tuning fork. If f is the frequency of first tuning fork, then the frequency of last, that is 64th tuning fork can be, let me take it as f dash. So, f dash is the tuning fork 64th tuning fork frequency, f dash is equals to, so first frequency plus, so total after, if I take the first tuning fork f and remaining the tuning forks are 64 minus 1, how many number of bits they are forming? 4. That means f plus first tuning fork frequency plus remaining tuning forks are 64 minus 1 into the number of bits formed by them with the neighboring tuning fork is 4. So, I can write last tuning fork frequency as f, that is the first tuning fork frequency, plus 64 minus 1, that are remaining tuning forks, into number of beats they are forming with the next tuning forks, that is 4. So, f plus 64 minus 1, 63 into 4. Now, simplifying this, f plus 4 into 3, 12, 4 6 24, 24 plus 1 25. So, 252. So, f dash, that is last tuning fork frequency, f dash equals to first frequency plus 252. Give it as equation number 1. So, by using first condition I arrived at one equation. Now, let us use the second condition, that is the frequency of last tuning fork. So, that is f dash according to our solution. So, f dash is the tuning fork frequency, that is last tuning fork frequency, that is equal to octave to the first one. Octave means, remember here octave means if suppose octave means 2 times that frequency, that means if f is the first frequency, f dash is the last frequency, octave means it is f dash is equals to 2 times f. So, here this is the second condition. Now, using first and second conditions I can get the value of f, that is so using this. So, here f dash is equals to 2f, I can use this equation 2 in equation 1, that is 2f is equal to f plus 252, then f is equal to 252. So, this is the first tuning fork frequency value, 252 Hz is the first tuning fork frequency value. So, now I can find the frequency of any tuning fork in the combination using this value. Now, let us find out. So, in our question we have to find the frequency of 16th tuning fork. Now, let us find out the required value, that is frequency of 16th tuning fork. So, let me take it as f 16, that is frequency of 16 tuning fork is equals to. So, we can take first tuning fork frequency plus. So, if I take a 16th one, so after, because I am taking the first frequency and after that how many will be there. So, 16 minus 1 15. So, f first frequency plus 16 minus 1 into number of beats which they are forming with the next tuning fork, that is 4. That is the answer will be f value 252 that we calculated plus 16 minus 1 15 into 4. So, that means 252 plus 15 4s are 60. So, it will be 312 Hz. So, this is the answer for this problem. So, remember after finding the first tuning fork frequency, you can find any frequency in the given series combination of tuning forks. For example, if you want to find a 12th frequency, F12 is equal to first frequency plus 12 minus 1 into number of bits they are forming. So, you will get 252 plus 12 minus 1, 11, 11 for 44. So, 252 plus 44, you will get 296 hertz. So, like that you can find out any frequency after getting the value of first tuning fork frequency in this method. So, remember this is one of the important methods regarding beats concept in this chapter. Okay. Next concept is, so in the last class I forgot to discuss the concept of end corrections for open and argon pipe. Now, let me cover that concept, and next I will start the Doppler effect. So, end corrections. End corrections. So, if you consider the open pipe or closed pipe, I told you that at open end always antinode will form, and at the closed end always node will form in case of open and closed pipes. So, here if you take the formation of antinode for a open end of a argon pipe, generally theoretically I am taking the antinode formation exactly at the end of the pipe like this, but practically because of inertia of the particles when they reach the end of the pipe, the antinode will form slightly above the open like this. So, this is actual theoretically the formation of antinode, but practically this will be the situation. The antinode will form slightly above the open end of the pipe. So, to find the exact value of frequency, we need to consider this end value. That means, this length of the pipe, this length. So, from here to this antinode exactly forming. So, this value to be considered to get the exact value of frequency of the vibrations of air column in open argon pipe and closed argon pipe. So, if you take a open pipe, so we know that the frequency of open pipe F open is equals to some NV by 2L. NV by 2L. So, this is theoretical value, but if I include the end corrections, so in case of open pipe there are two ends open. So, I need to add 2 times the end correction value. So, if I say this value of end correction is E, this is E, and this side also E. So, here the end correction value is experimentally determined as E is equals to 0.6 R, where R is the radius of pipe, radius of the cross section of pipe. So, if R is radius of cross section of pipe, the end correction of the end correction is equals to 0.6 times radius. Now, as open pipe is having two ends open, we need to include the both sides end correction. Then the correct value of frequency for the open pipe is equal to F open, that is N into V divided by 2 into L plus 2E, where E value 0.6 R, that is equal to N V divided by 2 into L plus 2 into L plus 2 into E, that means 2 into 0.6, it will be 1.6 R. So, this is the formula with the end correction, the formula for frequency with the end correction for an open pipe. Similarly, if you consider the closed argon pipe where one end is open, the frequency of a closed argon pipe including end correction is given by N V divided by 4L actually. So, I need to consider the end correction, so which is E. So, E is equal to again 0.6 R. So, 4 into L plus E or N V by 4 into L plus 0.6 R. So, in some problems they will mention the end correction value, including the end correction value. This is the formula for calculating frequency. Remember, for open pipe it is NV by 2 into L plus 1.6 R, where N is 1, 2, 3 and so on, they are harmonics. But in case of closed pipe, N value is only odd number 1, 3, 5, 7 and so on. So, that is the concept of end correction. So, including end corrections, these are the frequency formulas for open pipe and closed organ pipe. Now, let us move on to the next important concept, that is a Doppler effect in sound. Doppler effect in sound. So, the Doppler effect is one of the important concepts in the point of view of NEET exam. So, the definition of the Doppler effect. Okay. First, let us define Doppler effect. So, it is the phenomenon of apparent change in the frequency of sound when there is a relative motion between source of sound and the listener. For example, if this is a source which is producing sound, and later here is the person, that is a listener who is listening this sound, and this is the sound direction which travels towards the listener. If both are at rest, for example, source producing sound, some music system is playing at this particular location, which is the source of sound, and somewhere here the listener is at rest. Let the listener's speed, that is observer speed, is 0, that means he is at rest, and source also at rest. Let me take Vs is equal to 0, that is the speed of source is also 0. If both are at rest, the actual so the listener will receive the frequency which is the actual frequency of source. Suppose if source is moving towards the observer, so here this particular source which is producing sound is approaching the observer, in that particular case he receives more frequency than the actual frequency of source. That is due to relative motion between observer and the source, the frequency which the listener is listening is increasing. So, that phenomenon of apparent change in frequency due to relative motion between the source and the listener is known as a Doppler effect in sound. And here the other case also possible, if source is at rest, observer is moving towards the source or away from the source, the frequency received by the observer will be different compared to the actual frequency of the source. That apparent change, remember it is the apparent change which is which is not actually happening. So, the source frequency f and the frequency received by him will be different because of relative motion, whether source and observer are moving towards each other or away from each other, that frequency will be different. So, that phenomenon of apparent change is known as Doppler effect. Now, let us discuss this Doppler effect in each and every case. First case, and before discussing this Doppler effect, let me explain some conditions to study the Doppler effect. First we need to assume that the surroundings must be having no wind flow, that means the wind speed 0. So, air must be still in the surroundings, first thing I need to assume. And the second thing is the speed of source and speed of observer must be less than speed of sound. So, these are the two assumptions you have to consider before discussing the Doppler effect. Remember, speed of the wind must be 0, that means air must be still in that particular medium, in that particular surroundings where you are studying Doppler effect. And the other thing is the speed of source and the speed of the observer must be less than the speed of sound, and these are the two conditions. Now, assuming these two conditions, now let us discuss the Doppler effect in each case one by one. First case, the first case of Doppler effect is first case when source is moving, source S is moving and observer at rest. Source is moving, observer at rest. So, let me draw one diagram. So, this is the source which is producing sound, and S is the source, and observer somewhere here the observer. So, observer speed is 0 because observer is at rest, and let the sound is traveling in this direction. So, V is the speed of sound, which is given by f lambda, where f is frequency and lambda is wavelength of sound. So, f frequency of sound, frequency and lambda wavelength. Remember, actual frequency and actual wavelength of the sound waves produced by the source. Now, let the source is approaching the observer with a speed Vs. Let Vs is the source speed. So, if this is the case, now let us at t is equal to 0, let the source release the first wave of wavelength lambda. Remember, at t is equal to 0, before means at the time when it started moving, the source released its first wave and its wavelength is lambda, that is observed by the observer. Now, after releasing the first wave, we know that the time taken to release one wave, or the time taken for one oscillation, is called a time period. The capital T, time period of the source, time period of source, that is the time taken to release the first wave. So, after releasing the first wave, and we know the source is moving. So, let the initial position of the source is S. So, in that time capital T, that is time taken to release the first wave, the source will move to some new position. Let that new position is this one. Let the source reach this position in the time when it released the first wave. So, this distance S dash. So, from this new position, the second wave will be released by the source. Now, let this distance, we know that the speed of the source is Vs, and the time taken to move from S to S dash is t. Therefore, the distance S dash is equals to speed into time taken. So, give it as equation number 1. Now, as observed by the observer, the source is releasing the waves from its new position S dash. So, he will observe a wave whose wavelength is slightly less now. That means, according to the observation of the observer, the wavelength of the source now is, let us say, lambda dash, which is the apparent wavelength, okay, that is observed wavelength by the observer. So, that observed wavelength is given by lambda dash is equals to. So, what is actual wavelength? Lambda. How much distance it moved in releasing the first wave? S dash, that is Vs into t. So, the new wavelength that is observed by the observer is lambda dash, that is equals to actual wavelength minus the distance moved by the source in the time span of one time period, that is Vs into t. So, this is the distance moved, or that is S dash value. Now, this is called apparent wavelength, and we know that time period is equals to 1 by frequency of the source. Reciprocal of frequency is time period. Substituting that value, lambda minus Vs by f. Now, taking LCM will get f lambda minus Vs divided by f is lambda dash value. Now, f lambda is V, that is V is equals to f lambda, that is speed of sound. Therefore, apparent wavelength lambda dash is equals to V minus Vs divided by f. So, this is equation number 2. Now we know the apparent wavelength. Remember, this is observed wavelength by the observer because of the motion of the source towards the observer. That is what I am calling apparent wavelength. Now we know apparent wavelength, so we can find the apparent frequency that is observed by the observer. Now let us get that value. So if f dash is apparent frequency, if f dash is the apparent frequency, f dash is equals to, so f is equals to v by lambda, we know that formula, frequency is equals to wavelength, velocity by wavelength. So if f dash is the apparent frequency, that is equals to speed of sound divided by apparent wavelength lambda dash. So using that equation 2, in this equation I will get a v divided by v minus vs divided by lambda f, that implies f dash is equals to f into v by v minus vs. So this is the apparent frequency when source is moving towards the observer. So this is the first case and the value of apparent frequency due to Doppler effect. Similarly, if I take the other case, it means let me write here. Suppose if source is moving away from the observer, so this is the source and this is observer here whose speed is 0, who is at rest, and the source moving away from the observer with a speed Vs. Then in this case the apparent frequency can be obtained by just replacing this minus with the plus sign. That means if I write that frequency as f double dash, that f double dash is equals to f into v divided by v plus Vs. So this is apparent frequency when source is moving away from the stationary observer. So if I combine both, I can write a single equation. So when source is moving either towards the observer or away from the observer, that apparent frequency f apparent is equals to f into v divided by v minus r plus Vs. So this is the apparent frequency value when source is moving. So when source is moving towards the observer, take minus sign. When source is moving away from the stationary observer, take a positive sign. So you can calculate the apparent frequency value due to Doppler effect. That is what the first case of Doppler effect. Now let us discuss the another case of Doppler effect when observer is in motion, source is at rest. The next case of Doppler effect is the second case, observer is moving, observer moving, source at rest. So observer is moving towards a stationary source. So let this is the source S which is at rest. So I can take Vs is equal to 0 and here is the observer who is approaching the source with a speed say V naught. Now source is moving towards the observer is moving towards the source, and here as the source producing sound, that sound will travel towards the observer in this direction with a speed V is equal to f lambda. V is equal to f lambda, where f is actual frequency of source and the lambda is actual wavelength of the source. Now if you observe clearly the speed of sound towards right, so if I take right side as positive direction and left side it will be a negative direction. So here as the observer is approaching the source with a speed V naught, he receives the waves with a relative speed of V minus V naught, because so observer is moving in opposite direction, I am taking negative sign here. So V minus V naught, which is the relative speed with which the observer is receiving the sound waves. So he receives the sound waves with the relative speed of V plus V naught. So here let me write clearly, so this relative speed, the relative speed of receiving sound by the observer observer is equals to V minus of minus V naught, that is V plus V naught. So, if he is at rest, he receives the waves with a speed V, that is actual speed of sound, that means there is no Doppler effect. So, if he started approaching the source, so he receives the waves very fastly because he is also moving towards the source, that is what the relative speed with which the observer is receiving the wave, means he will receive the waves more frequently than when he is at rest. That is the reason why he receives more frequency, and that is what we call apparent change in frequency of sound. Now, if f dash is the apparent frequency received by the observer due to his motion towards the source, that f dash is given by the speed with which he is receiving the waves V plus V naught divided by the wavelength. So, now using that equation, so that is lambda is equals to V divided by f, substituting here you will get the apparent frequency V plus V naught divided by V by f, that is equals to f into V plus V naught divided by V is the apparent frequency value. This is the value of apparent frequency when observer is moving towards the source at rest. Similarly, if he is moving away from the source with a speed V naught, then the apparent frequency is given by f into V minus V naught divided by V. So, this is the frequency when observer is moving away from the source at rest. So, if I combine both the cases, f apparent is equals to f into V plus or minus V naught divided by V is the apparent frequency value. So, remember, when observer is moving towards the source, take positive, when observer is moving away from the source, take negative. So, V plus V naught by V one case and V minus V naught by V in another case. So, this is the second case of the Doppler effect in sound. So, let me write the formulas once. So, first case, source moving, observer at rest. So, O means observer, S means source. So, when source moving, observer at rest, the apparent frequency is given by f into V divided by V minus or plus in Vs. This is the frequency. So, minus sign you can take when minus sign you can use when source moving towards observer at rest, and take positive sign when source is moving away from the observer. This is the first formula. Similarly, the second case that I discussed is when observer moving source at rest. Again, in this case the apparent frequency is given by f apparent is equals to actual frequency into V plus or minus V naught divided by V. So, here positive sign when observer is moving towards the source, and minus sign when observer is moving away from the source, So, these are the different cases of Doppler effect in sound. Now, if both are moving, so let us see how to calculate the apparent frequency. That means, if both source and observer are in motion, how to calculate the apparent frequency. Remember these formulas, make a note of them clearly. So, next case of Doppler effect is, let me take third case. when both source and observer are moving. This is a general case of the observation of Doppler effect. When both source and observer are moving, the apparent frequency is given by f into so you take V plus or minus V naught divided by V minus or plus Vs. This is the formula for apparent frequency. Remember, depending on whether both moving towards, for example, if I generalize this one for this particular example, when the source and observer are approaching each other. So, these both are moving together towards each other. So, if both are approaching, now in this case the apparent frequency can be written as f apparent is equals to f into. So, remember, when observer is moving towards the source, so you can take V plus V naught, because the speed with which observer receives the waves will be V minus of minus V naught. So, it will be numerator, it can take V plus V naught divided by denominator. So, as the source is moving towards the observer, now first if I take only observer motion as considered, the relative speed with which observer receives the waves will be V plus V naught, and in denominator, as source is moving towards the observer, the value of denominator will be V minus Vs. So, this is the frequency when source and observer are approaching each other. When they are moving away, that means if source is moving and observer is moving, means they are receding away from, they are moving away from each other. In this case, this is the source speed and this is observer speed. In this case, the apparent frequency is given by f apparent is equals to f into. So, as observer is moving away, the relative speed with which he receives the waves will decrease, that means V minus V naught in numerator, and here source is moving away from the observer. So, here in denominator it can be V plus Vs you can take. So, this is apparent frequency. So, two cases when both source and observer are moving. Remember, in all these cases we assumed that the source and observer are along same line. Source and observer are along same line. So, these are generally in NEET this kind of problems only you can expect regarding Doppler effect. So, if they are not along same line, suppose if source is moving in this direction, observer moving in a different direction, then how to find the apparent frequency value we will discuss in the next class. It means in the next class I am going to discuss the finding of Doppler, that is apparent frequency when source and observer are not moving along the same line, and the other cases of Doppler effect. So, the source moving in a circle and observer moving in a circle, how to find the apparent frequency. The next case of Doppler effect is when so we already discussed three cases, when source at rest, source moving, observer at rest, observer moving, source at rest, and again we discussed the case of Doppler effect when both source and observer are moving together and moving away from each other. So, these are the three cases we discussed so far. Now, the fourth case is if source is moving in this direction with a speed say Vs, and the observer is not along the line of the source, means the observer is moving in this direction with a speed V naught. So, in this case, how to calculate the apparent frequency due to Doppler effect, let us see. So, this is the direction, this is called line of sight, this is the line of sight direction between the observer and the source. Let the direction of speed of source, that is the direction of motion of the source making an angle theta 1 with this line of sight, this is called line of sight, and let the direction of observer motion is making an angle theta 2. Now, you take the component of the speed Vs along the direction of line of sight, that is Vs. So, this component, so this is making an angle theta, this component of speed of source is Vs cos theta 1, and this component, so this is the speed of observer in this direction, and this component, the component of observer speed along the line of sight is V naught cos theta 2. So, now you can find out the apparent frequency. See, you can imagine a source moving towards the observer with a speed Vs cos theta 1 and observer moving towards a source with a speed V naught cos theta 2. So, now by taking this as the speed of source and this as the speed of observer, you can find the apparent frequency for this case as F apparent is equals to actual frequency of source into, so observer moving towards the source. So, if V is the speed of sound, so V plus observer speed V naught cos theta 2 divided by, so and source is moving towards the observer, so that it can be written as V minus the speed of the source, in this case is Vs cos theta 1. So, this is the formula for calculating the apparent frequency when the source and the observer are not moving along same line, that means they are moving in different lines. So, you can take a line of sight direction between source and observer and define the angles, and then find out the component of speed of source and observer using that angles, that is Vs cos theta 1 is the component of speed of source along the line of sight, and V naught cos theta 2 is the component of observer speed along the line of sight. So, taking both these components, you can find out the apparent frequency by using this formula, that is F into V plus V naught cos theta 2 and V divided by V minus Vs cos theta 1. That is the another case of finding apparent frequency. Now, let us see next case of Doppler effect, that is, so let me draw the diagram for the next case. Suppose if observer is at the center at rest, center of a circle, and the source is moving in a circular path with a speed Vs. So, let the speed of the source is Vs. So, if you observe carefully, the direction of, that is the line of sight, the direction between, so this is observer and this is V naught is equals to 0. The line of sight is perpendicular, that means the direction of motion of the source is perpendicular to the observer, that is the radius vector. So, in this case there will be no Doppler effect, because if you take apparent frequency F apparent, just now we discussed that formula, that is F into, so observer speed is 0. So, V divided by V minus Vs cos theta. So, in this case the angle between the direction of motion of source and the observer, the line of sight is 90 degrees. So, cos 90 0. So, Vs cos 90, that will be 0. So, it will be F into V by V, that means the observed frequency is equal to actual frequency, that means there is no Doppler effect. So, similarly, if observer is moving in a circular path, and source is at rest at the center, then in this case also theta is 90. So, there will be no Doppler effect, that means the apparent frequency is equal to actual frequency. So, remember these two cases where there is no Doppler effect. Now, let us see another case, that is a fifth case. When source is moving in a circular path with a speed say Vs, if r is radius of the circular path, you can write r omega, where omega is angular speed of rotation, angular speed of rotation of the source in the circular path, V is equals to r omega. Let the observer is somewhere here. Okay. Now, let us find out the maximum and minimum frequency values as the source is revolving in the circular path. Okay. So, when the source is at this point, it is moving away from the observer. Let this is point A, where source is moving away from the observer at rest, and when source comes to this point, the source is moving towards the observer. So, we know that when source is moving away from the observer, the apparent frequency will be less than actual frequency, and when source is moving towards the observer, the apparent frequency will be more than actual frequency. So, here when it is revolving in the circular path, this point will give the maximum apparent frequency value, and at this point the observer receives the minimum apparent frequency value. So, now let us find out f maximum and f minimum. That is f maximum at B, apparent frequency will be maximum, that f maximum is equals to, as the source is moving towards the observer, I can write apparent frequency as f into V divided by V minus Vs, and at point A frequency will be minimum because source is moving away from the observer. So, that frequency is given by f into V divided by V plus Vs. So, sometimes they will give the value of angular speed of the rotation of the source in the circular path. So, when they give omega value, so you can use this formula Vs is equals to r omega. So, you can substitute wherever it is required. So, that is another possibility of asking question about these frequency values when the source is moving in the circular path. Next, so let us sometimes the question will be about the number of beats heard by the observer with respect to maximum and minimum frequency. So, in this case you can take the difference between the two frequencies, that is FB is a beat frequency with this maximum and minimum frequencies, means how many possible number of beats with the maximum and minimum frequencies when source is moving in the circular path. So, you just take the difference between maximum and minimum frequencies, that will give you number of beats per second that are possible with these two frequencies. It is f maximum value fv divided by v minus vs minus fv divided by v plus vs. So, taking fv common, you can get this denominator LCM will be v square minus vs square, and here v plus vs minus v plus vs. So, it will be, so v minus v will cancel, vs plus vs 2 vs. So, it is 2 f v into vs divided by v square minus vs square is the beat frequency, that is number of beats per second that are possible when these two frequencies are sounded together. So, that is also another possible question based on this particular concept. Remember, and when source is at point B, it is moving towards the observer who is at rest here, and when it is at point A, it is moving away from the observer who is at rest. So, just I am using the frequency from the direct concept, that is f apparent is equals to f into v by v minus vs when it is moving towards the source, sorry, moving towards the observer, and the other case f minimum which is equals to f into v by v plus vs when moving away from the observer. So, this is the fifth case of a Doppler effect. The next case is when source is moving towards a wall, that this is a wall, source is moving towards a wall, let this is the source moving towards the wall with a speed Vs, and observer is behind the source. Simply you can say when when source is in between wall and the observer, when the source is in between wall and the observer. So, let us see how to find the apparent frequencies by the actual that is direct sound and the reflected sound. That means first, so the apparent frequency due to the direct sound, that means here observer at rest, let V naught is equal to 0 and source is moving away from the observer. Now, the apparent frequency in the actual sound or the direct sound is given by, so let me take it as F direct that is equals to F into, because source is moving away from the observer, that is F direct is equals to F into V divided by V plus Vs, V plus Vs you will get. This is apparent frequency due to Doppler effect in the actual sound. Now, the sound will reflect back, so it will reflect and it will be coming in this direction with a speed Vs after reflection. So, this is reflected sound. Now, the Doppler effect in a reflected sound, because you can imagine this as a virtual source of sound with a speed from which the which is moving with a speed Vs. Therefore, the apparent frequency due by the reflected sound wave, that is apparent frequency of the reflected sound wave observed by this observer is, so because this sound is moving towards the observer, then the frequency is given by F into V divided by, so source is moving towards the observer with a speed Vs. So, I can take V minus Vs. So, this is apparent frequency in a reflected sound and this is direct sound. So, these are the two formulas. Again, the question may be about how many number of beats are heard due to by how many number of beats possible with these two frequencies. That means, if you take the difference between this direct that is the apparent frequency in the direct sound and the reflected sound, how many number of beats are possible. So, that type of questions also we can expect. So, just to take the difference between the two frequencies, so then you will get the number of beats just like in the previous case. Okay, that is it. Next case is when observer is in between source and the wall. So, next case is when observer is between source and wall. Now, let us see how to find the apparent frequency in this particular case. So, observer is in between the moving source and the wall. So, this is the wall and here is the source moving with a speed Vs and somewhere here observer who is at rest. So, he is standing in between the moving source and the wall. So, in this case if you consider this one, this actual source is moving towards a stationary observer. So, the apparent frequency by direct sound is equals to F into, because source is approaching the observer at rest. So, I can take F into V divided by V minus Vs. This is a apparent frequency due to Doppler effect in direct sound, and this sound will reflect and it will come in this direction. Again, this if you take it as a source of sound which is moving with a speed Vs, if you observe carefully, in this case also source is moving towards a stationary observer. That means, the frequency, that is the apparent frequency due to Doppler effect in reflected sound is also given by F into V divided by V minus Vs, because this sound will hit the wall and it will reflect back. If you assume this as a virtual source of sound which is moving with a speed Vs, so then it can, the same case will arise. Here a source is moving towards the observer, here also a source is moving towards observer. So, the frequency will be same in both the cases when observer is standing between a moving source and the wall. So, that is the case of Doppler effect. So, if you try to calculate the number of beats here, no beats will be heard because same frequency is there. So, because difference will be 0. So, that number of beats will be 0. So, this is another case of Doppler effect.